Alright, let's take a look at problem 7. Calculate the amount of work necessary for the reversible isothermal expansion of 1 kilogram of steam from 10 bar to 5 bar at 400 degrees C, and then calculate the amount of heat associated with this process. Alright, so as I look at A, immediately two ideas come to mind. Right, one, in my opinion, is going to be easier than the other. Okay. So first, they want us to calculate the amount of work necessary for the reversible isothermal expansion, right? Isothermal being key, of 1 kilogram of steam from 10 bar to 5 bar at 400 degrees C. So the first thing that comes to mind is if I want to calculate the work, right? So we're not told anything about shaft work, so we can assume reversible PV boundary work. So work then would be the negative integral of P dV, okay, from my initial to my final state, right? From my initial state to my final state, okay, where I know that in my initial state, so I'm going to presumably be my superheated steam tables, right? And we could confirm that in a second, okay. But what I could do is I could go to my superheated steam tables, and I could read off. What would I have to do? So I would need to. So I would read off my, say, molar volume or specific volume at 10 bars and at 5 bars. And then what I would do is I would tabulate molar volumes as a function of pressure between 5 and 10 bars. And I would need to numerically integrate that data. All right, so I could do it. So at 400 degrees C, okay. So at 400 degrees C, I could go to my superheated steam tables, and I could calculate data for P, all right, in bar versus specific volume in meters cubed per kilogram. All right, and we had a problem like this in chapter 3, and then I could use, say, trapezoid method to numerically integrate. Right, I could do that, right, and that would work, right, and all would be good. Okay, so that's option 1. Option 2, which I think it's probably going to be easier. Okay, and I should point out, right, this only works because it's an isothermal process. And so in order to integrate this, I need to know how P changes with respect to V. Right, I need to know P is a function of V. And so the fact that we need to hold T constant so that I can think of P as just a function of V. Otherwise, if I have a single component, single phase system, I have two degrees of freedom. I would need to have, I would need to know how temperature is changing as well, right? So that only works because temperature is held constant. All right, but if I think about, reversible isothermal expansion, okay, in the context of chapter 4, and now I'm thinking about entropy. All right, so what I'm thinking about is I know that ds is equal to Q reversible over T. Right, my heat exchange for reversible process. Okay, and so if I have an isothermal process, right, I have T ds, and this should be dq is equal to dq reversible, so that T times the integral from my initial to my final state ds, which is equal to T times S2 minus S1, is equal to Q reversible. Okay. Now, the benefit of this is, since I know the temperature and pressure of my initial state and the temperature and pressure of my final state, right, for this isothermal process, I can look up S2 and S1 in my superheated steam tables. Right, S is just a state function, and once I have S, I could calculate the change in S, and I could calculate Q. All right, and then once I have Q, well, then I can go to my first law of balance, all right, and I know that delta, so first let me box this in, delta U is going to be equal to Q plus W, okay, where Q is going to be T times S2 minus S1 plus W. So I would end up getting, for this reversible process, that W is equal to delta U, Okay, and so I'm going to write U2 as U2 minus U1 minus T times S2 minus S1. And where I think this is easier is that U and S are both state functions, so since I know the initial and final conditions of my system, I could just look up those values in the steam table and compute differences as compared to tabulating data and numerically integrating. Okay, so this should work in terms of allowing you to calculate W. Okay, but personally I think that this will be easier. So let's go ahead and let's look up the data and let's compute. And so let me write down my state variables. Okay, so I need T1 and P1. So T1 is 400 degrees C and P1 is 10 bar. So we're at 400 degrees C and 10 bar. Okay, and note that T1 is equal to T2 is equal to T, right? So I just have T up here. And so, maybe even just let me just call this T. Okay, and then, well, just T2 is equal to T1, and I'm just going to call it T is equal to 400 degrees C. And my final pressure is 5 bar. Okay, so now I can go to my steam tables. So I'm going to go to my superheated steam tables. So they're saturated. Let's go to superheated. All right, and so first thing at 5 bar, my saturation temperature is 151.84. So my temperature is greater than Tsat, so I know I have a superheated vapor, and same is true at 10 bar. Okay, so at 10 bar, I'm going to go over to 400 degrees C since I'm at 400 degrees, and I'm going to read off U, and I'm going to read off S. Okay, so U is 2957.8. U1 equals 2957.8. And S1 is 7.4668. Okay, so U is in kilojoules per kilogram. S is in kilojoules per kilogram Kelvin. Okay, then let's look up U2 and S2. So that's at 5 bar. So at 400 degrees, U2 is 2963.6. And that's kilojoules per kilogram. And S2 is 7.7954. And that's kilojoules per kilogram Kelvin. All right, so then computing. Okay, so we'll go up to MATLAB. We'll create a new script. And so let's tabulate. So let's do, so U1 was 2957.8. S1 was equal to 7.4668. U2 was 2963.6. 2963.6. S2 was equal to 7.7954. And T is 400 degrees C, but we need to convert to Kelvin, so I'm going to add 273.15 Kelvin to it. Okay, got it. So then from our equations, all right, Q is just equal to T times S2 minus S1. And W is equal to U2 minus U1 minus Q, which is TS2 minus S1. Okay, so I'll just save this here for now. Okay, but if we run it, all right, for Q, we get 221.1971. That's kilojoules per kilogram. And W is negative 215.3971 kilojoules per kilogram. So let's write down the values, and then let's see if they make sense in terms of the sign. So 221.1971. Again, I'm going to apologize for the stylus. The semester's too short, so probably be all done by the time a new one comes in. So negative 215.3971. And that's kilojoules per kilogram. Okay, so W is negative, so that means that work is done by our system. Q is positive, so it means heat's added to our system. And so we have reversible expansion. And so expansion, so negative work makes sense. And so then heat's required to expand our steam. All right, so all makes sense. So this is the route I would go to solve it. Again, you could have created or tabulated PV data, and you would have tabulated that data between 5 and 10 bar at 400 degrees C. All right, so between 5 and 10 bar, so at 5 bar, here's 400 degrees C. You could calculate or tabulate V, and then you can do that all the way up to 10 bar, and then you should be able to numerically integrate the data. And this works because T is constant. All right, because I'm integrating P with respect to V, so I want P only to be a function of V. All right, and so since temperature is fixed, temperature is constant. All right, I fix a intensive variable. I have just a single degree of freedom, and that works. All right, and I should be able to do it. I like this approach though because I feel like it's a lot easier just in terms of looking up data at those single state points and taking a difference. Hope that helps. Let me know if you have any questions.